Hello everyone, my name is Anushka Shukla and today I'll be presenting on the topic visualization of vector field and flow data. This topic helps us understand how complex dynamic systems are analyzed through visuals. Let's dive in. Here is a roadmap for my presentation. Introduction to data visualization. Need for vector and flow visualization. What is a vector field? Its mathematical representation. Scalar versus vector fields. What is a flow data? Types of flow. Techniques to visualize vector fields. Color and texture mapping. 2D versus 3D visualization. Tools and libraries. Application, challenges, future trends, and conclusion. So let's go. Data visualization is the graphical representation of data, making complex data easier to understand. It allows us to spot trends, patterns, and anomalies. In computer graphics, this is especially important for analyzing dynamic phenomena like air movement, fluid flow, or even biological systems. For example, meteorologists use wind fields visualizations to predict weather conditions. Now, why do we need to visualize vector and flow data? Because they represent both direction and magnitude and change over time and space. This is very crucial because of predicting behavior like storms or blood flow, for design simulations such as airflow over a car, for educational models to teach physics or fluid mechanics. For example, car manufacturers use these visualizations to improve fuel efficiency by studying drag. So now let's learn about what is a vector field. A vector field assigns a vector to every point in space. Each vector has magnitude and direction. Think of wind flow. At each point in the air, there is a speed and a direction. Some real world examples include electric fields around charged objects, water currents in oceans, and magnetic fields around magnets. Now let's learn about it mathematically. Mathematically, a vector field is written as f of x, y, z equating to u, v, w. Here, u, v, w are the components of the vector in 3D space. Let me give you one example. If we take f of x, y, z and equate it to minus y, x, 0, this represents a rotation around the z-axis in the xy plane. This kind of representation is used in simulations like airflow over airplane wings, as we have already discussed in above examples. Now let's compare scalar versus vector fields. A scalar field has only magnitude, like temperature, 45 degrees Celsius at a point. A vector field includes both magnitude and direction. For example, wind, 5 meters per second northeast. Scalar fields are visualized using color maps, while vector fields use arrows or streamlines. So now that we have learned this, let's learn about flow data. What is flow data? Flow data describes how particles like fluid or air move across space and time. They follow key parameters. These key parameters include velocity, pressure, or direction. These are used in fluid simulations, aerodynamics, or even human respiration studies. Now let's learn about its types. It is categorized as steady flow, in which properties don't change with time. Example, water from a calm tap. In unsteady flow, properties do change over time. Example, wind during a thunderstorm. In laminar flow, there is smooth and orderly layers. Example, syrup slowly pouring. In turbulent flow, we have irregular and chaotic movement, like smoke from a bonfire. So, how do we visualize it? We follow these visualizing techniques like glyphs, which are arrows at grid points to show direction and magnitude. Streamlines are the lines that show the path of a fluid at a fixed time. Path lines trace the path of a single particle over time, and streak lines connect particles that pass through the same point over time. Example, streamlines are used to study airflow over airplanes in real time, as we have discussed above. Now let's learn about color and texture mapping in flow visualization. Color mapping uses gradients like red to blue to show velocity or pressure. For example, red for high speed and blue for low speed. Texture mapping, especially using LIC, which is line integral convolution, it helps in visualizing subtle flow patterns that might be missed with arrows. For example, weather simulations often use both techniques to show wind intensity and direction. Now, let's learn about 2D visualization versus 3D flow visualization. 2D visualization is easier to interpret and useful for surface flows like wind maps or news channels for weather forecasting. 3D visualization adds depth, realism, and it is used for volume rendering in medical or engineering fields. But it's it also has its challenges like higher memory, computational cost, and visual clutter. Let's take an example. In a 3D visualization, blood flow inside a 3D heart model is much more informative than a flat image, but it does has its challenges as discussed before. It can cause higher memory, high computation cost, visual clutter, etc. So now that we have learned about these visualizations, let's learn about some tools on how we can use it to plot or visualize it. These tools are like ParaView, which is open source and great for large data sets. We have TechPlot and OpenDX, which is CFD focused tools. We have MATLAB, which is good for quick vector field plotting, and then we have VTK with Python for developers building customized pipelines. These tools are used in industries ranging from aerospace to environmental science. Now let's learn about the applications. Vector and flow visualization is applied in many fields, such as in weather forecasting, in which predicting storm paths and using wind vectors uses visualization. In engineering, it is used to design better cars and planes. In medicine, it is used to visualize blood flow in arteries. In gaming, it is used to visualize real time fire, smoke, and fluid effects. But it also has its challenges. Its challenges include large data leading to slow rendering, difficulty in interpreting 3D vectors due to clutter, and need for real time interactivity. Now, but it also has future scope, and these future trends include GPU acceleration for faster performance, AI based simplification for better clarity, and VR AR integration for immersive visualization. Hence, it has its applications, challenges, and future trends. Now, let's move on to the end of this presentation to the conclusion. To conclude, vector field and flow data visualization helps decode complex systems visually. Techniques like streamlines, glyphs, and color mapping bring invisible forces to life. Tools like ParaView and MATLAB make this easier and more interactive, and hence making visualizations and flow data visualization and vector field visualization much easier and much accessible. Thank you so much for listening.